Alright guys, welcome back. Today we're finally going to talk about pn-junctions. So we're finally getting into some real application. We spent 10 episodes talking about theory behind semiconductor physics, deriving different equations. Now we're actually going to put that to use and look at a real device that's used in electronics. So we're going to start with this N-type silicon, right? N-type meaning donor doped, meaning it's doped with atoms uniformly that have some kind of that have an extra electron, right? And then through a process called diffusion. Nowadays they use something called ion implantation, but the olden days they would well, not that old. I mean, they still do it in some fabs, but they would coat this top layer with a photoresist, and they would create a hole for it, or create an opening right here, and then they would grow they etch it, etch away the photoresist, and then they would grow an oxide. So you would have this oxide like this. And oxide has very, very low diffusivity, right? It's very hard to diffuse anything into oxide compared to silicon. So then what they would do is they would use this carrier wafer, that's had a very high concentration of whatever acceptor atom you want to use. Maybe it was a boron or something like that, and it's a very common acceptor doped atom. And we would diffuse, and we would create this well right here, which is p-type. Now the process is a little bit more complicated than I just said, but we just need to know that what we have is this p-type well in this n-type region. And what happens here is, if we just zone in on this little differential of a region right here, where this is p-type and this is n-type, such that this line is just a straight line, and we kind of superimpose that right here, we have a pn-junction, right? And before we calculated the Debye length, and we showed what happens when there's an abrupt change of doping in any kind of semiconductor material. It leads to band bending, it leads to a very small built-in potential, and it leads to this region that's depleted of free carriers, right? And so what happens here? Let's look at a big view. So over here we have this N bulk with some doping Nd. And over here we have the P bulk with some doping Na, right? So, and we assume 100% ionization, non-degenerately doped semiconductor. So all these donor ions become ionized, and all of a sudden you get this huge concentration of free electrons in this N side over here. And then similarly we get this huge concentration of holes in the P side over here, right? Pn, right? So naturally diffusion takes place, right? Electrons will diffuse over to this P region. Similarly, holes will diffuse over to this N region. And in between, we get this region that is essentially depleted of all charges, of all mobile charges. So, and what happens is, the holes diffuse over here, and they kind of build up, but then they decay exponentially. Why do they decay exponentially? Because they're minority carriers in a sea of majority carriers, and they have some characteristic minority to carrier diffusion length. So as they go further and further into the bulk, what happens is this holes that diffused over here will just recombine, and they won't be there anymore. And another way to look at this is like this. This is this is just a rough sketch. These are your holes. Minority carrier holes, we'll call this P of N because it's in the N region, and they diffuse all the way to P naught. And what is P naught? Well, from the law of mass action, which assumes non-degenerately doped semiconductor, and at equilibrium, P naught is simply, or Pn naught we should say, is simply Ni squared over N and D, our doping. Similarly, over here, the electrons which diffuse from the N side over to the P side, they decay and fall off here like this, N of P to N of P naught, which is, you guessed it, that's right, Ni squared over Na, right? Minority carriers will eventually diffuse, or will eventually recombine and go back to their intrinsic level right there. And then in this region right here, which we call the depletion region, we have no carriers, essentially. I mean, they're carriers, but they're so small with respect to doping that we can just say that the free carriers go to 0. So in this region right here, we only have our donors, which is our acceptor doping, which is Na minus, and over here, our donor atoms, which is just Nd plus, right? And kind of rewrite this here. So we have, this is our x-axis. We call this, we'll call this negative xp, we'll call this 0, and we'll call this xn. So the whole width of depletion region is xn plus xp. This is our x-axis, right? So, high doping here, free electrons from this donor dope that diffuse over here. Over here, acceptor doping, these free holes diffuse over to the right side, and we get this characteristic depletion region, and then this high level of acceptor doping minority carrier holes, which decay as we go into the semiconductor. And similarly over here, high concentration at this edge xp of minority carrier electrons, which of course go to 0 as they go into the bulk and they recombine with these this incredibly large number of holes that are in this region. So what happens here is let's look at this in terms of the Fermi level before we get into the equations. So we have an area of high constant of p doping. Well, let's just draw the Fermi level here. There's our Fermi level EF, right? And in one region we have acceptor doping, right? Well, that means our valence band is very close to the Fermi level, right? And then over here, in our N side, N doping means Fermi level is very close to the conduction band. You know, high concentration of electrons, low concentration of electrons, high concentration of holes, right? And it bends exponentially just like this. And we're going to be able to show mathematically why this is all true, but we shouldn't have a physical meaning before we do all that. That's N negative XP, just like that. And in this bulk, we just have ND, and in this bulk we just have Na, plus concentration of holes, and this plus concentration of electrons, and in here it's just Nd, and here it's just Na, right? All right, minus and plus, because we assume 100% ionization. Okay, so let's look at some other, we'll look at one equation here, and from this we can kind of get a general idea of some stuff that's going on here. So if the only charges in this region are negatively ionized, I think that's anions, anion acceptors in this region, it's just positively charged cation donors. Then if we were to graph our charge density rho, it would look something like this. Where this is x, this is xn, this is negative xp, and then this right here is negative q and a, and this right here is q and d. Right, just like that. And from the Poisson equation, we know that d squared of phi over dx squared is equal to negative de over dx, which is equal to negative rho over permittivity of the semiconductor epsilon silicon, right? And so that means from this relation we know that to get electric field from this, well, it's just the integral, right? Because E from this E is equal to integral of rho dx, right? So if I rewrite this over here, well, if you integrate this constant right here, well, it's just negative slope right there, right? And on this side, when we integrate this constant right here, it just becomes, it's in the positive, so it becomes a positive slope right there. This is electric field, and this is x. So you see our electric field changes as we go across x, starting at negative x of p, which is 0, and x of n where it is 0, all the way to the what we call the metallurgic junction, which is this right here, where it maxes out in what we call E of M, maximum electric field. Right. So because of this depletion region, we get an electric field that changes as we go across. Right. And similarly, if we integrate again, if we integrate the negative again, we get potential, right? So if I integrate this one more time, I get potential phi, which would just go something like this. And then stop right here. Negative xp, xn. So this means we have some built-in potential right there. So these are the basics. This is the physics without getting into any real math, but you just gotta kind of take all this in. It's a lot of interesting stuff. You see, we were able to get charge from here and here, and from that we were able to get electric field, and from that we're able to get this built-in potential. So let's, and the other thing is this region here where the minority carrier concentration falls off. We call this the quasi-neutral region, right? Because it's outside the depletion region, but we call it, quasi, because there is this gradient, there is this change in carriers as we go down here, and that's ultimately what's going to contribute to the current when we look at these PN diodes. So let's do some math now. So now that we derived, or we talked about the basic physics behind pn-junctions, now we're actually going to derive some of the values that we're going to need that are going to help us in evaluating these devices. This is what we know so far. We know we put an N region and we dope N-type and P-type together. We get this depletion region, we get this band bending right here, and we get this built-in potential. And just a little kind of common sense thing that we should remember, anytime the band bends down like this, it means that we have an area that's negatively charged, positively charged. Well, electric fields always go from negative to positive like this. So something that's always helped me is to remember the electric field always goes into the hill, into the upward curve right there. And we know from the Poisson equation that if our electric field is negative, then our potential is always going to be positive. So this VBI is really to think about our built-in potential. It's the sum QBI is equal to the built-in potential in the N region plus the built-in potential in the P region, right? Where this right here is the built-in potential in the P region, this is the built-in potential in the N region. And here's N always equal. This is true under almost all conditions. N is equal to Ni exponential EF minus EI over KT. Similarly, holes are equal to Ni exponential EI minus EF over KT, just like that. We consider this just to be in the N region and this to just be in the P region. So you can write this as EIN, right, and this is EIP, right? And so this equation corresponds to this region over here, and this equation here corresponds to this region over here, right? So we wanted to go from here all the way to here. So let's derive these. So in this case, EI, so it's and N. So in the bulk, this N is just equal to ND, right? And in the P bulk, this P is just equal to NA, right? So we want to find expressions for EIP and EIN, and hopefully when we put this together, the Fermi level disappears, cancels out, because the Fermi level is just something that we kind of take in reference to everything, and we don't really, finding it mathematically isn't going to work because it's an unknown in this case. We know KT, we know NI, we know NA and ND. Our two unknowns are EIN and EIP. and EF. So we're hoping EF goes away. So in this case, we rewrite this EIN is equal to KT. I'm sorry, it's negative KT natural log of ND over NI plus EF. Similarly, over here, EIP, this is just doing algebra. You look at this, and if you can do the algebra in your head, maybe I can, I don't know. Yeah, it's just NA, or KT natural log NA over NI plus EF. Alright, let me double check this. Okay, looks good. All right. So, to find this total energy, you want to know EI. This is EI, right? Right. This is EIP, right? This is EIN, right? Built-in potential, another way to look at it, is it's 1 over Q EIP minus EIN, just like that, right? So, when we subtract this from this, we get, erase that, EIP minus EIN is equal to 2KT natural log, I'm not going to jump ahead that far, KT natural log NA over NI plus EF minus becomes a plus, KT ln ND over NI minus EF. Sure enough, just as we hoped, EF cancels, and we can combine this two to equal to KT natural log ND over NI, right? Well, that's this. Built-in potential, we have to divide by Q, right? Q goes right here. That is our built-in potential, right there. KT over Q times natural log NA and D. So what does that tell us? If NA and ND are both very, very high, we get a very large built-in potential, right? If NI is very, very large, we get a very small built-in potential. When would NI be large? Well, large bandgap semiconductors have a very small intrinsic energy level. So naturally, they're going to have a smaller built-in potential, right? Also, it's, dependent on temperature. As temperature increases, this built-in potential is going to increase. So, yeah, that's our built-in potential. That's it.